Welcome to the deep dive, where we take the densest, most complex sources, the foundational texts of global knowledge, and extract the critical insights you need to be truly well-informed.
Today, our mission is a little different and I think really exciting.
It really is. We are performing a deep dive into the fundamental concepts of cognitive science, but with a twist. We're strictly confining ourselves to a single alphabetical section of a major encyclopedia.
And it sounds restrictive, I know, but the sheer breadth of concepts captured by just this one letter is, well, it's astonishing.
Yeah.
We'll be moving from the macro level of human culture, evolutionary biology, and classical philosophy, right down to the neurophysiology of sleep, the algorithms of AI, and even the developmental anomalies of the brain.
That's why this is such a powerful exercise. The goal for you, our dedicated learner, is simple: to gain a rapid, comprehensive, and above all, conceptual understanding of these interdisciplinary terms.
Right, we want to cut through the jargon.
Exactly. Identify the key theoretical tension points and give you the intellectual tools to connect these really diverse domains.
So to manage this, we've organized the material into three core arenas. We're going to start by looking at how intelligent systems, both human and artificial process, organize and optimize information. So that's going to cover concepts like decision trees, dynamic programming, and dynamic approaches to cognition.
Then we're going to pivot to the core human capacities. This is where we confront the foundational questions of what defines intelligence, perception, and morality. We'll be looking at giants like Descartes and Darwin, and diving into the mechanics of deductive reasoning and depth perception.
And finally, we'll turn our attention to how context fundamentally shapes the mind. We'll analyze external influences like culture, social dominance, and discourse,
Right.
alongside the profound internal context of neurochemistry and development, as explored in, say, dreaming and dyslexia.
That sets a demanding, but I think a really thrilling agenda. So let's unpack this, and let's start at the widest possible scope, the external context that defines what we know and how we know it: culture.
Okay, so we can define culture pretty straightforwardly as, the set of knowledge, beliefs, and behaviors shared within a group.
Sure.
But for cognitive science, the crucial angle is the relationship between this shared information and the individual mind.
And this brings us to this fascinating view of culture as an information economy. This idea, pioneered by Roberts back in the 60s and then refined by Boaster, proposes that cultures aren't just these passive containers for stuff.
Right, they're not just repositories.
They are active, dynamic systems that create, distribute, and utilize information. They are, in essence, economies built on knowledge.
And this framework immediately connects cognition to sociology. I mean, Durkheim, ages ago, talked about the division of labor.
Right.
Boaster argues that how labor is divided, so how specialized the tasks within a group are, fundamentally dictates how knowledge is stored and how efficiently that knowledge can be retrieved when it's needed.
So if knowledge is the currency, then the culture provides the banking system and the exchange rate.
That's a great way to put it.
A powerful example of this is the concept of explicit cultural models of error.
Precisely. If you look at complex, high-stakes tasks, flying a commercial aircraft, performing a complex surgery, even something like trap shooting, the culture has formalized a specific shared model of what constitutes an error.
It provides the standard for what's right and wrong.
Exactly. The evaluation criteria and the procedural corrective actions. This shared model standardizes the cognitive process across different minds. Without that cultural agreement on what an acceptable error or a critical failure looks like, the system, whether it's a cockpit crew or a team of surgeons, it just breaks down.
This also helps explain variation within a culture, right? Boaster's model of intracultural variation seems essential here.
It is. It proposes that variation is a direct result of different learning opportunities.
So can you walk us through the two poles of that model?
Certainly. So at one pole, you have domains with high agreement. These are areas that are either observable by direct universal inspection, like basic folk biology, classifying local plants and animals, or domains accessible via introspection, like color classification.
Okay.
Because ample, equal learning opportunities exist for everyone who interacts with the environment, you see very high cross-cultural and intercultural agreement.
It's readily accessible knowledge.
But then you have the other pole, where the knowledge is really dependent on who you talk to.
And that's where you see high variability. If a domain like complex mythologies or religious doctrine or specific traditional medicinal knowledge, if it's learned only from others and it's not independently verifiable through observation,
then what you know depends on who you know.
Exactly. The knowledge distribution literally reflects the social communication network. You only know what your direct social links have passed down. The social structure literally dictates the content of your mind. This leads us to one of the most compelling insights in this section. The extension of this idea into distributed cognition, which was laid out so well by Ed Hutchins in 1995. This is where we stop viewing the mind as being purely constrained by the skull.
hmm Hutchins views whole social groups operating in complex environments as single computational engines. And this cognition is distributed not only among the human agents, but also among artifacts.
So things like a navigation chart, a compass, or even the layout of a tool, these aren't just external memory aids.
No, they're active components in the system's thinking process. That's the key shift. These artifacts store, transform, and transmit information in ways that exceed the capacity of any single human brain.
Like a checklist in a cockpit.
A perfect example. It's an artifact that guides and structures the collective memory and planning of the pilots. It's effectively performing a cognitive function. The mind that successfully flies the plane is the collective tool-using system, not just the pilot's brain.
That's profoundly important. It connects cognitive science, how the individual mind processes information, with anthropology, how society structures that process. It shows that the engine of cognition is often this collective tool-using system, forcing us to look outside the boundaries of the individual. So if culture defines the environment of our cognition, then Charles Darwin. Well, he defined the biological foundation of the cognitive engine itself. His theory of evolution by natural selection is arguably the single most important biological theory of the last century and a half.
Absolutely. His work provides the necessary foundation for the entire field of evolutionary psychology. Before Darwin, it was very hard to conceive of the rational mind or moral behavior as having a biological selectable basis.
We often summarize his life so quickly, but the source really emphasizes the journey. His education, the 5-year HMS Beagle voyage where he collected all these specimens and geological data, starting from a position of, biological orthodoxy.
And that orthodoxy began to truly collapse when he got back and started making sense of his specimens. Specifically, the various species of mockingbirds he had collected across the Galapagos Islands in March 1837. He realized the variations weren't random.
They were systematic.
Systematic and island-specific. But the mechanism, the engine of selection, that didn't click until 1838.
Right, that was the catalyst.
That's right. The catalyst was reading Thomas Malthus's essay on the principle of population. Malthus's grim observations on population pressure and the struggle for existence in human populations gave Darwin the missing piece of the puzzle, a ruthless, constant selective force operating in nature.
The genius of Darwin, and what makes him so relevant to our field, is that he refused to exempt the human animal and mind from this process.
He was heavily influenced by empiricist thinkers like David Hume and even his own grandfather, Erasmus Darwin. He viewed intelligence not as something magically separate, but as a generalizing and loosening of the cerebral structures that underlie instinct.
So our complex reasoning basically emerged gradually.
Yes, through inherited habits that were refined and selected over countless generations. He detailed this in The Descent of Man in 1871.
And what was the central mechanism he proposed for the evolution of the human mind?
He argued that the mind reached its highly complex human form primarily through natural selection, but importantly, it was accelerated by the emergence of language. Language, in his view, produced heritable modifications in brain patterns, allowing for faster and more complex cognitive organization to be passed down.
But the most profound cognitive contribution might be his explanation for moral behavior and altruism. This really challenges a lot of modern, purely gene-centric views.
It really does. Darwin proposed that moral instincts were acquired not just through individual selection, but through community selection. His argument was brilliant. A self-sacrificing behavior might slightly disadvantage the individual agent.
But it helps the group.
It benefits the clan, which includes relatives and allies, significantly. And the competitive advantage of the collective outweighs the individual cost.
Exactly. So clans with more altruistic instincts that are more cooperative and mutually supportive would have a critical advantage in competition and survival against other groups. This gradually elevates moral conscience in the species.
And this model contrasts significantly with later, more individualistically focused sociobiology, which often emphasizes purely utilitarian selfishness or direct genetic fitness path.
He also provided a foundational text for ethology, the study of animal behavior, with his 1872 work, Expression of the Emotions in Man and Animals.
That book explained emotional instincts, fear, surprise, anger, solely through the inheritance of acquired habit. It provided a completely biological, non-supernatural framework for studying fundamental emotional reactions across species.
So Darwin established the biological constraints and the evolutionary pressure that built the cognitive structures we study today. It's the ultimate why behind the what. Okay, so the cognitive structures Darwin built perform one central task constantly: decision-making. This is the process of choosing a preferred option from alternatives. Sounds simple, but it is fundamentally complicated by uncertainty and preference conflict.
And the study of this is incredibly interdisciplinary. It pulls from economics, statistics, psychology, political science. We're going to focus here on individual choice behavior, which is traditionally analyzed through three lenses.
Let's start with the ideal, the normative approach.
This assumes the rational decision maker. This entire framework is built on a priori considerations, on mathematical axioms. It says if you have well-defined, consistent preferences that obey these axioms, you will choose rationally. This is the foundation of rational choice theory. It's the benchmark.
But then reality steps in, which is the descriptive approach.
The descriptive approach is empirical. It observes how humans actually choose, and it quickly revealed that our choices systematically and predictably depart from that normative model. We are messy, contextual, and often contradictory.
And finally, the bridge between the two is the prescriptive approach.
The prescriptive approach is applied. It focuses on developing methods, training, algorithms, heuristics to help real-world decision makers make choices that align closer to the normative, rational ideal.
When we make decisions, we're usually dealing with uncertainty. But the source material differentiates two crucial types of uncertainties.
Yes, we have to distinguish between risky decisions, where the probabilities are known like rolling dice or buying an insurance policy, and ambiguous decisions, where the likelihood is unknown and you have to rely on subjective judgment, which, of course, characterizes most real-world choices.
And this leads to our risk attitudes. Let's revisit Bernoulli's classic explanation of risk aversion to gains. Most people prefer a sure $100 over a 50% chance of $200, even though the expected value is identical. Why?
Bernoulli explained this way back in 1738, using the concept of diminishing sensitivity. It was formalized by the concave utility function. The subjective value or utility of the first $100 is subjectively worth more to you than the utility of the second $100.
Ah, okay.
So because the subjective value of the sure 100 is higher than the subjective expected value of the gamble, which is half the value of 200, you choose the sure thing.
An expected utility theory from von Neumann and Morgenstern in 1947 made this the ultimate normative benchmark. If you're rational, you maximize subjective expected utility.
But the descriptive studies found a fascinating symmetry when looking at losses. People display risk-seeking for losses. If you're faced with a sure loss of $100 versus a 50% chance of losing $200, most people choose the gamble.
Which means the diminishing sensitivity applies in the domain of losses too, but it results in a convex function.
That's right. The emotional pain of the initial loss is severe, and the marginal pain of the subsequent loss is less so. So they gamble, hoping to entirely avoid that initial, very painful sure loss.
These findings were systematically captured by prospect theory, the tremendously influential descriptive theory from Daniel Kahneman and Amos Tversky in 1979. This is the bedrock of modern behavioral economics.
And it has three core properties that explain why we deviate from rationality. The first is reference dependence.
This is critical. Rational theory focuses on total wealth. Prospect theory focuses on changes in wealth gains and losses relative to a dynamically shifting reference point, usually the status quo. You don't evaluate the absolute final outcome, you evaluate the movement away from where you started.
The second is loss aversion, which is maybe the most powerful force they identified.
Absolutely. The value function is significantly steeper for losses than for gains. The subjective displeasure of losing $100 is psychologically much more powerful than the pleasure of gaining $100. Losses literally loom larger.
And the third property is the resulting S-shape of the value function, which just visually captures this entire behavioral departure. Concave for gains, which is risk aversion, and convex for losses, which is risk-seeking.
When these risk attitudes are manipulated by language, you get framing effects, which are normatively problematic because they violate the consistency required for rational choice.
Yeah, Tversky and Kahneman showed that just how a problem is described as a gain or as a loss can completely reverse people's preferences.
I think we need a concrete example here to make this really stick. Let's say an airline is thinking about adding a $50 fee for check bags.
Okay, if they frame it as the ticket costs $400, but you get a $50 discount if you don't check a bag there using a mainframe. This encourages risk-aversion people prefer the sure gain, the discount.
But if they frame it as, the ticket costs $350 plus a $50 penalty if you check a bag, they're using a loss frame.
And that triggers risk-seeking. People will gamble that the penalty isn't worth avoiding. And despite the final cost being identical, the description changes the decision.
This violation of description invariance shows just how fragile our preferences are.
And the problem just gets worse, and multidimensional choice decisions involving conflicting attributes like job prestige, salary, or apartment location. Here, the weight you assign to each attribute is highly contingent on immaterial changes in context. It shows that we don't walk around with perfectly stable, well-ordered preferences. We actively construct our preferences in the moment, and we're heavily influenced by context.
The relevance is huge. Process tracing studies have replicated these deviations in real-world settings, how physicians select treatment, how people save for retirement, even how taxi drivers stop working based on a target income theory rather than maximizing their total return. So moving from the flawed, contextual human decision maker to the perfect computational classifier, let's look at decision trees. This is a fundamental and I think really accessible tool in machine learning.
It really is. A decision tree is essentially a graphical representation of a procedure for classifying or evaluating something. It's basically a flowchart for logic.
It maps instances or examples from its domain, like patient records, to elements of its range, like a class label live or die, or a numerical value for regression trees.
The structure is hierarchical and simple to follow. You start at the root node. Internal nodes contain a test, a question about a variable like, is the patient receiving steroids? The branches are the outcomes of that test, yes or no. You just follow the branch to the next node until you hit a leaf, which contains the final classification.
The example of forecasting hepatitis outcome illustrates this perfectly. By applying tests based on liver condition or bilirubin levels, the tree just directs you to a predictive outcome.
And the great attraction of decision trees is their clarity. They're highly interpretable. They show you exactly how classification was reached, unlike, say, an opaque neural network.
Right.
They're also easy to construct automatically from labeled instances using algorithms like C4.5, and you can easily convert them into human-readable IFN rules.
The construction process is key. It's recursive and top-down. How does the algorithm decide which test to put at the root node?
It employs a greedy search, which means it looks locally for the best immediate split. The algorithm only stops and turns a node into a leaf, which is called pre-pruning, if the instances remaining in that node are sufficiently pure, meaning they almost all belong to the same class.
And in the internal node step, the algorithm has to select the optimal test. We use heuristic functions for ranking these tests, right?
Yes. For classification trees, the goal is to produce the smallest, most predictive tree, so heuristics minimize entropy or impurity. Functions like information gain or the GNI index measure how well a potential test partitions the data into pure classes. The best split is the one that reduces entropy the most. For regression trees, the goal is to minimize variance.
Now, a critical issue for any learning algorithm is overfitting. How do decision trees suffer from this, and how do we fix it?
A tree can become overly complex, fitting noise or outliers in the training data, rather than the true underlying pattern. This means it performs brilliantly on the training data, but miserably on unseen data. This is where post-pruning comes in.
So post-pruning happens after the tree is fully grown.
Exactly. You then use a separate set of data, the pruning set, to systematically reduce the tree size by merging branches or turning internal nodes into leaves.
This is a practical way to manage the bias-variance trade-off.
That's the one. A smaller pruned tree has higher bias. It's a coarser partition of the data, but it has lower variance, meaning it generalizes much better to new data. You are sacrificing a little accuracy on the training set for much better predictive power in the real world.
And finally, a huge improvement came with the use of ensembles of trees.
Correct. Rather than relying on one optimal tree, ensembles like random forests or boosting techniques build multiple individual trees. Since the errors of these individual trees tend to be independent, voting or averaging their predictions significantly improves overall accuracy and robustness.
So they're a foundational component of modern computational decision-making systems.
Absolutely.
Okay, we've seen the computational ideal in decision trees, but let's return to the human mind and a fundamental type of human reasoning, deductive reasoning. This investigates our ability to recognize entailment.
An entailment is a very specific, strict, logical relation. It means that the conclusion must be true whenever all the premises are true. The classic example is, All men are mortal. Socrates is a man, therefore Socrates is mortal. The conclusion is necessary.
And deductive logic systems provide the normative standard for correctness. Psychologists test this by giving subjects arguments and asking them if the conclusion follows logically.
But here's the complication. Real-world human thinking isn't constrained by strict logic, it's constrained by communication. This is where pragmatics and conversational implicature come into conflict with logic.
Right. Grace's work from 1989 showed that ordinary conversational settings impose restrictions that can override or supplement entailments. We expect speakers to be maximally informative.
So consider the statement, some of my in-laws are honest. Logically, the term some means at least one, and it's perfectly compatible with all of them being honest.
But no one ever hears it that way.
No. Because the speaker is trying to be maximally informative, the listener automatically generates the implicature that if the speaker knew all of them were honest, they would have said all. Therefore, the listener infers that some must be dishonest.
And experimental results show that when subjects perform logical tasks, they often use these natural language conversational principles. This leads them to reject deductively sound arguments, or accept deductively unsound ones, because they're relying on the plausible implicature.
Which raises a serious conceptual difficulty for cognitive scientists. If people routinely blur the line between necessary entailments and merely plausible inferences, do they possess a proper concept of entailment in the first place?
It's not just the subject's fault, though. The ambiguity of the instructions interpreting logically follows, as the natural language therefore clouds the results. Plus, logicians themselves use many systems. Rejecting a principle might just mean the wrong logical standard was applied to the specific domain, like time or obligation.
This leads to two competing views on the nature of entailment in the mind. The first is the unified set view.
This suggests that people automatically translate natural language into a single underlying logical form, and a single set of inference procedures operates on that form. Our intuitions should be consistent, even if performance is limited by memory or attention.
The second view suggests varied intuitions. This posits that there are many different logical concepts, and subjects engage in a kind of model fitting, selecting the mental inference package that makes the argument come out right for the specific context of the problem they are solving.
So this debate is central to the architecture of thought. It's asking whether we are fundamentally logical creatures whose performance is degraded by external factors, or if we are fundamentally pragmatic creatures using logic as just one tool among many.
From the invisible architecture of reasoning, let's pivot to the foundational sensory task of constructing our physical reality, depth perception. This is the ability to perceive the three-dimensional layout of the world, a problem that plagued philosophers like Descartes because the retinal image is, by definition, only two-dimensional.
Descartes himself attempted to solve this with early kinesthetic cues back in 1637. He suggested that we compute depth from internal muscular adjustments, the change in the lens's accommodation, or focusing, and the degree of convergence, how far the eyes turn inward.
And while these are important, they have a severe limitation. They only vary significantly within a meter or two. They primarily apply to near space or personal space, anything within arm's reach. We obviously perceive depth accurately much further out.
So the most important information source for far distances, what's called ambient space, must be the spatial context and the layout of objects. This is where James Jerome Gibson's analysis comes into play.
Gibson, in the 50s and 60s, focused on how the layout of surfaces on a ground plane provides incredible information. If the ground is homogeneously textured, the resulting texture gradient in the visual field provides a scale in the optic array to compare relative distances. If the size of the texture unit is known, it can even specify absolute distance.
And maybe the most powerful static cue is the relationship between objects and the horizon?
Yes. The horizon is the locus of vanishing points of parallel lines on a plane. The angular extent between a surface location and the horizon specifies the absolute distance relative to your eye height. Your own visual geometry provides a constant reference frame.
Beyond layout, we use object properties. Interposition or occlusion, when one object hides another, gives an immediate ordinal sense of depth. Object A is closer than object B.
Right.
And binocular occlusion, where a part of an object is hidden from only one eye, can even start to elicit a sense of metric depth.
And while relative size is an excellent cue for comparing distances between similar shapes, the source notes that the familiar size of an isolated object is generally not a reliable cue for distance. We don't rely on knowing the exact size of a known object floating in space to tell us its distance.
The other major category involves a dynamic viewpoint. parallax cues.
We have motion parallax, which is the successive change in projection as you move. Nearby objects appear to move quickly against distant backgrounds. This is almost as effective as stereopsis for densely patterned surfaces.
And the most celebrated depth cue is binocular parallax or stereoscopic vision, which relies on the simultaneous difference in viewpoint from our two horizontally separated eyes. Wheatstone discovered in 1838 that this generates a powerful, vivid relief.
Stereoscopic acuity is incredibly precise, responding to differences as small as 10 to 30 arc-seconds of disparity. But this precision declines rapidly with distance. Since disparity decreases so fast, the brain must somehow scale the depth response based on the absolute distance to the objects, though the exact mechanism for this scaling in far space is still unclear.
The whole enterprise of depth perception beautifully demonstrates how the visual processing streams are required to integrate diverse, often ambiguous information sources, both monocular and binocular, kinetic and static, to construct the stable, three-dimensional reality we inhabit. We mentioned him earlier in the context of depth cues, but now let's give René Descartes the focus he deserves. He is the figure who defined the foundational problems that cognitive science is still grappling with today.
Descartes dominated the mid-17th century by proposing a radical anti-Aristotelian mechanist theory of nature. His ambition was massive: to explain all biological and many psychological phenomena like reflexes, muscle contraction, even some learning, using universal mechanistic physics based only on quantifiable concepts: size, figure, and motion.
He literally wanted to turn the body and all non-human life into a grand machine.
Precisely. This led to his notorious mechanomorphism, the view of the non-human animal, the brute, as an animal automaton, a self-moving machine. This is the origin of the ongoing philosophical critique against advocates of animal consciousness.
But the famous contribution, and the source of 2 centuries of debate, is his dualist conception.
He argued for a sharp distinction between the physical, extended body, res extensa, and the rational soul, or mind, res cogitans, which he saw as an immaterial entity endowed with innate intellectual concepts. This places him squarely as a major figure in nativism.
To justify this hard boundary, the presence of an immaterial principle in humans, he proposed 2 decisive tests that animals uniformly failed, as he outlined in Discourse on the Method.
The first was the adaptive response. An automaton, or animal, like a bird building a nest, demonstrates a highly specialized instinctual skill. But it fails the test of responding adaptively and inventively to a variety of challenging, novel circumstances. Its actions are fundamentally limited and predictable.
The second, and perhaps the more famous, was language use.
Yes. The ability to use true language, structured, versatile, and flexible enough to express our thoughts to others, was the unique sign of the rational soul. He drew a crucial line between mere cries or grunts and the kind of language required to convey a vast, open-ended range of human thoughts.
We see his methodology in the Meditations, where he approached reason from a radical first-person perspective, applying deep skepticism.
He argued that all perceptions of the physical world, everything we sense, is subject to doubt. But he realized that the act of doubting required an agent, leading to the indubitable conclusion: I think, therefore I am.
This established the mind-body distinction and the perennial mind-body problem. How can 2 fundamentally different substances, the immaterial mind and the physical body, interact so closely?
Furthermore, he distinguished sensation versus reality. Color, for instance, is not a property of the body. It's a sensation in our minds, a psychological effect caused by matter and motion hitting the nervous system. This established his Cartesian theory of ideas, profoundly influencing later focus on mental representation.
But here's where the critique comes in, the tension within his own work. The source notes that Descartes strictly limited mental phenomena only to states accessible to an individual's conscious awareness.
Yet when describing the mechanics of vision and distance perception in his dioptrics, he clearly invokes a process of geometric calculation, a kind of computation that cannot possibly be conscious.
So he's implicitly needing a mechanistic, unconscious cognitive architecture to explain perception.
Even while philosophically arguing against it, yes. Descartes' work gave cognitive science its most crucial questions and its first great theoretical contradiction.
The moment we use language, the very thing Descartes argued separates the rational soul from the automaton. We enter the realm of discourse. Discourse is the ground of language, experience, and meaning, encompassing all verbal exchanges.
And what's critical is that individual utterances are often vague or ambiguous. Context is required to resolve that ambiguity. Discourse provides that context.
The source material gives us three ways to characterize this, moving from the observable event to the abstract structure. The first is discourse as event.
This focuses on the social character of the exchange, the human agents, the turn-taking mechanisms, which vary widely by culture, and how the exchange creates or reproduces social alliances. That's a focus common in anthropological linguistics.
The second is discourse as linguistic content, the text itself, the ordered string of words.
But the primary focus for cognitive science is the third, discourse as information structure. This is the complex, rich, structured information that is presupposed or conveyed, which is far richer than the literal words alone.
This information structure is multifaceted. It includes the participants, the linguistic content, the background information, and crucially, the intentional structure.
The intentional structure is the hierarchical organization of information linked to the speaker's inferred goals and the topics or questions being addressed. We use this full, contextual information to resolve ambiguities, grasp coherence, and understand the speaker's true intended meaning.
This emphasis on intention and context is why the traditional, static view of meaning equals truth conditions had to yield to pragmatic phenomena and dynamic theories.
That's the paradigm shift in the 1980s. Meaning is not static description. Meaning is context change potential. An utterance's meaning is the change it brings about in the shared information state of the interlocutors.
So in dynamic semantics, assertions update the proffered information, questions modify the intentional structure, and orders update everyone's commitments.
And we can't discuss meaning without grace and implicature. We rely on the fact that much of what we understand follows from what is said, given the assumption of conversational cooperation. The contemporary work highlights how the intentional structure is crucial for generating these implicatures, inferring the speaker's meaning that goes beyond the literal words.
This complex information structure is reflected in the linguistic features we use, topic-comment structures, prosodic prominence, which words we stress, and devices like anaphora, pronouns, and ellipsis, all of which ensure coherence and help track the common ground.
Discourse shows us that meaning is inherently dynamic, social, and dependent on a constantly managed context, moving far beyond the analysis of isolated sentences.
If the dynamic social exchange of discourse requires coherence, the internal belief system also craves it. Let's transition to dissonance, specifically Leon Festinger's 1957 theory of cognitive dissonance.
Dissonance theory posits that people are motivated to seek consistency among their cognitions, their beliefs, attitudes, and actions. When two or more cognitions are inconsistent, it causes an emotionally aversive tension state.
And the individual is then motivationally driven to reduce this tension. The total dissonance is quantified as a ratio. Dissonant relations divided by all relevant relations, weighted by how important the cognitions are.
And the methods for reduction depend heavily on the resistance to change of the cognitions. If an action is completed and can't be undone, the belief must change. The classic example is smoking. I smoke, and smoking causes disease are dissonant. Since quitting is highly resistant to change, the smoker may instead minimize the evidence for the disease or exaggerate the pleasure of the habit.
Three classic research paradigms emerged from this theory. The first is post-decisional dissonance.
After making any choice between mutually exclusive options, dissonance arises from the conflict. The chosen option has bad features, and the rejected option has good features. To reduce this tension, individuals rationalize their decision by exaggerating the advantages of the selected option, effectively spreading apart the alternatives.
And this effect is strongest when the decision is difficult and irrevocable.
The second is selective information seeking. Once a commitment is made, people are motivated to avoid information that conflicts with the choice and actively seek out information that supports it. While the evidence for this is mixed on the precise conditions, the motivation to protect the initial decision is clear.
The third, and arguably the most powerful demonstration, is insufficient justification or forced compliance.
This involves inducing someone to perform an action that is counter to their private attitude, but offering them minimal external coercion, a very low incentive. Dissonance arises because the action, say I just lied, conflicts with the attitude I am an honest person.
So because the external pressure, the incentive, is too small to justify the action, the only way to reduce the dissonance is to change the internal attitude to align with the behavior.
And this is the counterintuitive finding. The less external pressure you face to lie, the more your attitude changes. If you were paid $20 to tell someone a boring task was fun, you can rationalize. I did it for the money. If you were paid only $1, you rationalize. That wasn't enough money to justify lying, so I must have actually believed the task was fun.
This shows how a seemingly rational motivation consistency seeking can lead to profoundly irrational outcomes, forcing the mind to adopt beliefs that justify past behavior.
Modern research is focused on the mechanisms, specifically the physiological arousal and psychological discomfort that defines the tension state. It helps distinguish dissonance from non-motivational alternatives, like self-perception theory.
And research shows dissonance effects are often linked to threats to one's self-concept and can be alleviated by self-affirmation.
And now we even have computational models that treat dissonance reduction as a gradual constraint satisfaction process using artificial neural networks, suggesting it shares core mechanisms with memory retrieval or analogical reasoning.
Turning now to linguistics, let's explore the fundamental building blocks of language sounds. Distinctive features. These are defined as a universal set of binary features encoding the articulatory and acoustic properties of speech sounds. They're the primitives of phonology.
So a sound like T or N isn't a single unit. It's a bundle of feature values. For N, it's plus nasal, continuant, which means complete oral closure, and plus coronal for an elevated tongue tip. Remarkably, only about 20 such binary features suffice to describe the entire inventory of sounds found in all spoken languages worldwide.
This hypothesis, originating in the Prague School, is supported by three powerful arguments. The first is that features impose a constraint on sounds.
The physical capacity of the human vocal and auditory apparatus is enormous, yet the actual set of sounds used by human languages is relatively small. Distinctive features define the set of possible speech sounds by higher-level cognitive requirements, severely limiting the inventory.
His second argument is that features explain the structure of sound systems.
Features maximize the cross-classificatory effect. If a language employs one sound that belongs to a specific feature set, say, plus voice like B, D, G, it often utilizes all the sounds from that same set. They don't just pick sounds randomly, they select bundles of features.
And the third argument is the most crucial for modeling. Features explain phonological processes.
Right. Phonological rules, how sounds change in context, depend on natural classes defined by shared feature values, like plus voice or plus strident. Classes of sounds that are featurely arbitrary, like P, B, S, K, are almost never needed by phonological rules, demonstrating the cognitive reality of these underlying features.
Historically, the Prague School defined features in acoustic terms, what they sound like. But the seminal work, Chomsky and Halley's The Sound Pattern of English, SPE, in 1968, shifted the focus almost entirely to articulatory terms, descriptions of vocal tract configurations.
A major theoretical advance was autosegmental or nonlinear phonology, which suggested that features are independent objects, not strictly tied to a single segment in time.
The Torina language provides a great example of this, where the feature plus nasal can act as a separate abstract morpheme, a first-person prefix, that attaches itself to a sequence of sounds, effectively spreading across multiple segments.
And this led to concepts like feature geometry, where features are hierarchically organized into functional classes, like the laryngeal metafeature grouping together voice and other laryngeal settings.
And the most surprising confirmation of their cognitive reality came from studies of sign language.
Research confirmed that sign languages also utilize representations composed of distinctive features, like hand shape, movement, and location. This implies that the existence of a featural level of representation is a modality-independent cognitive principle, essential for structuring any complex system of communication, whether it's spoken or signed.
Distinctive features are the primitives of language. Now let's ask how those primitives, or any piece of knowledge, are physically stored and organized in the brain. This brings us to the debate over distributed versus local representation.
This is a foundational question of mental representation. Is a piece of information stored in one specific, dedicated location, or is it spread out over available resources? This debate goes back to the 19th century Gall arguing for dedicated discrete brain regions versus Flourens arguing for knowledge spread across the cortex.
The terminology is complex, a semantic mess, as the source notes, but we need to clarify the core distinctions. Let's contrast the extremes.
At one extreme is strictly local representation. This is the idea that an item, say the concept of apple, is represented by a single dedicated unit or neuron. The state of all other neurons is irrelevant to that representation.
The opposite is distributed, basic.
Here, Apple is represented by a distinct configuration pattern of activities spread over a large pool of units, and every unit in that pool participates to some degree. We can further distinguish between sparse distribution, where only a small proportion of units are active, and dense distribution, where a large proportion are active.
Then you have concepts relating to how those units define features. What's the difference between microfeatures and coarse coding?
Microfeatures means that each unit represents a very small, specific, local feature, like a specific angle of a line in an image. The item is the pattern defined by the collective activity of these microfeatures. Coarse coding is the inverse. Individual units represent features that are broad and overlapping.
Right, like tuning forks. One fork might respond to a range of frequencies, not just one. The concept of red might be represented by a pattern across several units that each respond strongly to slightly different overlapping shades of red.
Exactly. And the source gives us two fascinating concepts related to system efficiency. First, superimposition.
This occurs when two or more distinct items are represented simultaneously by the same distributed pattern. You see this in the synaptic weights of feed-forward networks that store many associations concurrently. It's highly efficient, but potentially messy.
And finally, equipotentiality, a term popularized by Lashley. Here, an item is represented by a pattern over a pool, and the pattern over any subpool up to a limit also suffices to represent the item. The classic analogy is the optical hologram, where every piece of the film contains the whole image.
In computational modeling, especially connectionism, why did the distributed approach become so compelling despite its complexity?
It offers huge advantages: greater capacity, content addressability, automatic generalization, and fault tolerance. If you lose a few units, you don't destroy the whole pattern. Plus, it seems biologically plausible.
But the disadvantages like catastrophic interference, where learning new knowledge immediately obliterates old knowledge, are serious drawbacks.
This led to the famous Fedor-Platian critique, arguing that connectionist models must implement the systematic, structural regularities of classical symbolic architecture, or they fail to explain the systematicity of human cognition.
Right, the idea that if you can understand John loves Mary, you can also understand Mary loves John.
Exactly. The connectionist response was that they can explain systematicity using distributed representations, but they encode complex structures non-concatenatively, meaning they don't explicitly string symbols together. The patterns themselves carry the relational structure. This suggests that distribution might be a third, fundamentally different category of representation.
The structure of representation leads naturally to the structure of the mind itself, domain specificity. This view holds that cognitive abilities, knowledge structures, reasoning modes, and acquisition mechanisms differ across distinct content areas.
And this stands in direct contrast to the older domain general position, famously championed by Piaget, which argued that we use a core, uniform set of abilities, like memory and inference, and simply apply them to whatever problem we encounter.
The evidence favoring specificity is compelling. Individual variation in cognitive level across domains. Neuropsychological dissociations, like losing the ability to recognize faces but retaining spatial reasoning. Innate cognitive capacities in infants. And powerful evolutionary arguments suggesting specialized mechanisms were selected for specific problems.
The source material outlines three distinct approaches that assume domain specificity, but they differ fundamentally in what they assume is innate and how they develop. Let's start with the most powerful, modules.
The modular approach, championed by Chomsky for language and Fodor for perceptual systems, argues the mind is a collection of separate, specialized subsystems, like a language faculty or a facial recognition module.
And Fodor's modules are innately specified, mandatory, fast, and crucially encapsulated. They're insensitive to central knowledge or general beliefs.
Meaning a visual illusion, like the Miller-Lyer illusion, still persists even though you know the lines are the same length. Your central knowledge can't penetrate the encapsulated visual module.
Exactly. The second approach is folk theories. This suggests that everyday thought is organized into theory-like structures for specific domains, like folk psychology, beliefs, desires, or folk physics, object substances.
The difference from modules is essential here.
It is. Folk theories have things like ontological commitments and domain-specific causal principles. But unlike innately constrained modules, they undergo radical restructuring over time and are heavily informed by culture and knowledge. Children's understanding of physics, for example, is radically reorganized as they develop.
And the third approach is expertise. This involves pockets of skill developed through extensive experience, resulting in unusual feats of memory and knowledge reorganization.
And the key point here is that expertise is narrowly specific. The classic Chase and Simon study from '73 showed chess experts have phenomenal memory for chessboard arrangements, but their general memory for randomly arranged digits is perfectly ordinary. The cognitive boost is strictly limited to the task domain.
So the relevance here is profound. The debate over these three types of specificity biologically constrained modules, culturally informed folk theories, or experience-driven expertise fundamentally shapes how we model learning, development, and the very structure of the mind. Moving from the structure of the individual mind to the structure of animal societies, let's explore dominance in animal social groups. This refers to situations where an individual or group controls or dictates the behavior of others, especially in competitive situations.
And dominance is fundamentally a predictive tool. It predicts the outcome of future interactions without them having to resort to costly fighting every single time.
The benefits for the dominant individual are concrete. Priority access to resources like food and resting spots, favorable grooming, protection, and usually higher quality mates. They also command the attention of others and show greater resistance to stress.
However, the source reminds us that the link between high dominance status and lifetime reproductive success is often debated and not always robust. Furthermore, there are costs, like the stress of defending resources, or the possibility of subordinates sneaking copulations while the dominant individual is distracted.
The concept itself is often considered ubiquitous but slippery, prompting conceptual challenges. Is dominance an inherent reality or just a construct imposed by human observers?
Or do these hierarchies even exist outside of highly constrained captive environments? These are all active debates.
Despite those debates, dominance remains a powerful organizing principle, often manifesting in three basic types of hierarchies.
The simplest are linear hierarchies or pecking orders, common in small groups. These are transitive. If A dominates B and B dominates C, then A always dominates C.
Then you have nonlinear hierarchies, where at least one non-transitive relationship exists, so the order of dominance isn't a simple straight line.
And finally, despotisms, where a single alpha individual dominates every other member of the group, and the dominance relationships among the subordinates are largely indistinguishable from one another.
The core cognitive question is, how is this status recognized and represented internally by the animals?
And preliminary research suggests animals are capable of constructing and agreeing upon ordinal relationships. Specifically, studies with non-human primates, like Cheney and Seyfarth's work, suggest that understanding dominance entails two complex cognitive processes.
Okay, what are they?
First, constructing and storing the ordinal relationships A is higher than B, B is higher than C. Second, applying transitivity using knowledge of others' social ranks to make deductions about individuals with whom they have not personally interacted.
This social knowledge is vital for complex social strategies like alliance formation. An animal needs to know who to recruit as an ally who is safe to retaliate against.
And how their intervention will affect the social balance, which may involve observation, deduction, and even a rudimentary form of theory of mind attributing mental states or ranks to others. The study of dominance provides a crucial window into social cognition in animals, probing the boundaries of insight, planning, and abstract representation in non-human minds.
From the complexities of social interactions, let's turn inward to the most profound internal context: dreaming. Mental activity is virtually continuous during sleep, but its characteristics shift dramatically between REM and NREM phases.
The discovery of REM sleep in 1953 fundamentally shifted the study of dreaming. Before, the focus was purely Freudian psychoanalytic interpretation of content, dreams as disguised, censored, unconscious wishes. Afterward, the focus shifted to explaining the formal characteristics of dreaming based on brain activity.
And the formal characteristics are strikingly different between the two states.
REM reports are typically 7 times longer, highly animated walking, flying, described formed, vivid visual images, and feature strong, often plot-linked emotions like anxiety or anger. And REM reports, by contrast, are more thought-like, dull, and fragmentary.
And the intensity and visual vividness correlate strongly with the EEG characteristic of REM activation.
They do. During this state, sensory gating occurs. The rising threshold to external stimuli protects the dream state, allowing internal stimuli to dominate.
This functional analysis led to the influential activation synthesis hypothesis in 1977.
Right. This theory completely mechanizes dreaming, attributing it to the automatic activation of the brain in REM sleep by a specified pontine brainstem mechanism. It explains the structural features. Internal stimulation of visual, motor, and limbic regions by brainstem signals accounts for the vivid hallucinations, the sense of movement, and the strong, raw emotion.
And the characteristic bizarreness of dreams, the non sequiturs, the sudden changes in location or character, is attributed to the chaotic nature of this internal autoactivation and the simultaneous failure of short-term memory due to chemical changes.
This neurochemical basis was refined in the AIM model, which stands for activation, input source, and modulation. The key to understanding dream consciousness lies in the modulation shift.
Okay, what is that?
In the waking state, the aminergic system cells containing noradrenaline and serotonin is tonically active. In REM sleep, these aminergic cells shut off. The brain is aminergically demodulated.
And this profound shift in neuromodulation accounts for the cognitive deficits we see in dreams.
Exactly. This demodulated state is what accounts for the bizarreness, the lack of logic, and the amnesia. Simultaneously, pontine cholinergic neurons become reciprocally activated, conveying eye movement information to the visual motor areas, which causes the hallucinated vision and movement, and to the amygdala, which causes the emotion.
Human brain imaging using PED studies confirms this. We see activation in the pontine brainstem, which is the organizer, and selective activation of the limbic forebrain, the mediator of raw emotion.
But critically, we see the selective inactivation of the dorsal prefrontal cortex. This area is vital for self-reflective awareness, critical judgment, and executive thought. Its suppression perfectly accounts for the characteristic cognitive deficiency of dreams, why we rarely realize that the bizarre scenario we are experiencing is illogical or impossible.
Dreaming provides a natural nightly window into consciousness, showing directly how small, subtle shifts in brain neurochemistry and regional activation dictate our entire mental state and cognitive function. The neurochemical dynamics of the brain in sleep lead us to the major theoretical challenge to classical cognitive science: dynamic approaches to cognition. This paradigm posits that natural cognition is fundamentally a dynamical phenomenon best understood in dynamical terms.
And this contrasts sharply with the classical view, the law of qualitative structure, which defined cognition as analogous to digital computation, treating the mind as a sequence of symbols being manipulated.
This dynamic perspective, tracing roots to cybernetics, gained popularity as frustration grew with the limitations of classical AI. The core model is the dynamical system model.
Right. An agent is conceptualized as a set of quantitative variables that change continually, concurrently, and interdependently over quantitative time, governed by dynamical laws, often expressed as differential equations.
So behavior isn't seen as a step-by-step algorithm, but geometrically, in a state space, a map of all possible mental configurations. Analysis uses concepts like attractors, which are stable states the system tends toward, transience, and stability.
This approach is particularly powerful for complex temporal processes like decision-making. Instead of modeling it as a rational choice algorithm, it's modeled as variables evolving interactively over time, which accommodates effect, context, and time pressure far better than classical logic.
The core philosophical break is the role of time. Cognition is not just something that happens over time, it is an essentially temporal phenomenon.
Time is continuous and quantitative. The timing details, the rates, synchronies, and precise flux of change are essential components of the cognition itself. It views cognition as a continuous co-evolution of the brain, body, and environment, not a sequential sense-think-act cycle.
And this connects directly to the emphasis on situatedness and embodiment.
Correct. Cognitive processes are collective achievements of brains and bodies in contexts. The dynamical language naturally integrates environmental changes, body movements, and neurobiology simultaneously. The environment is part of the system, not just an input source.
And representations themselves have to be reconceived in this model.
They shift from being static, context-free units to transient, context-dependent stabilities, temporary patterns of activity or trajectories shaped by an attractor landscape. Some researchers even pursue models that are entirely representation-free, focusing only on the flux of change itself.
The dynamic approach is thus a fundamental alternative to the traditional computational theory of mind, prioritizing the continuous, temporal, and embodied nature of intelligence.
While the dynamic approach gives us the underlying physics of continuous change, dynamic programming provides the highly effective mathematical tools to find optimal solutions within defined systems.
Dynamic programming is a general algorithmic technique for solving complex optimization problems by intelligently structuring them into a collection of smaller, dependent subproblems. The crucial technique is that it works backward through these subproblems.
Its main application is optimizing paths through state space graphs, particularly for planning optimal policies. Let's take the shortest paths problem as the core example. Finding the shortest path from any starting state S to a desired goal state G in a directed weighted graph.
The algorithm uses iterative improvement. We want to compute a distance function, d of s, giving the distance from every state s to the goal g.
We initialize d of s with a large overestimate for all states, except d of g is 0. Then, in a critical iterative loop, we update d of s to be the minimum of the immediate arc lengths LSA, plus the estimated distance from the resulting state.
So you're saying the best distance from here is the immediate step plus the best known distance from the next spot.
That's exactly. And after a number of iterations equal to the number of states, the distance function d of s converges and is correct for all states.
The immense power of this approach is that once d is computed, the optimal path, or policy, is described by simply choosing the action at any state s that minimizes d. The result is a policy mapping every state to its optimal action, not just a single brittle planned path.
And this framework generalizes perfectly to Markov decision processes, MDPs, where state transitions are stochastic or probabilistic rather than certain.
An MDP introduces a reward function and a stochastic transition function. The goal is to find a policy that maximizes the expected total reward over a finite number of steps.
And this is solved by working backward from the goal, calculating the value function VKS, the expected utility of being in state S, and executing the optimal policy for K-steps. The value V at any time is derived by calculating the maximum of the immediate reward plus the expected future utility of the next state distribution.
This framework is also the conceptual link to reinforcement learning.
Yes. Dynamic programming solves MDPs assuming a known world model. When the world model is unknown and must be learned through interaction, solving the MDP becomes the problem of reinforcement learning, which is often called stochastic dynamic programming.
This mathematical rigor is fundamental to AI and computational planning, providing rigorous methods for optimization and control under both certainty and uncertainty. Dynamic programming models optimal action. Let's shift back to language, where dynamic semantics models optimal information exchange. This represents a major paradigm shift in formal semantics starting in the 1980s.
The traditional static view was philosophical, meaning equals truth conditions. It was a descriptive, static relation between a sentence and the world, and interpretation was done sentence by sentence.
The dynamic view overturned this, stating, meaning is context change potential. The meaning of a sentence is the change that an utterance of it brings about in the context of the conversation.
And this shift was necessitated by real-world linguistic phenomena that static semantics simply couldn't handle, like speech acts, presupposition, and implicature, all of which stress the context-updating nature of language.
The classic illustration of this failure is the cross-sentential anaphora problem. Take the sequence. A man walked in, he was wearing a hat.
In a static sentence-by-sentence model, the indefinite noun phrase a man exists only within the first sentence. Yet the pronoun he in the second sentence clearly refers back to that man, binding across the sentence boundary. Static models lack the memory to connect them.
So two major dynamic theories address this. The first was discourse representation theory, DRT, by Camp and Heim.
DRT's dynamics is primarily representational. The dynamics lie in building and modifying representational structures called discourse representations. Referential expressions, like a man, introduce discourse reference with associated constraints, and subsequent anaphoric expressions like he pick up these already established reference.
The second, stricter implementation is dynamic semantics proper by Grunendijk and Stokov.
They located the dynamics in the concept of meaning itself. They assigned various expressions, such as the existential quantifier, a dynamic meaning that allowed its binding force to extend beyond its ordinary syntactic scope. The essential element that changes is the information state of the hearer information about entities, events, and their relations.
In this framework, the core notion of truth is replaced by support.
Right. An information state, S, is said to support a sentence if the utterance of that sentence does not change the state S.
And this gives rise to dynamic entailment. A sequence of premises entails a conclusion if and only if updating the information state consecutively with the premises leads to a state that supports the final conclusion.
Dynamic semantics is crucial because it models language as a fundamentally social and incremental tool designed to manage context and point of view, integrating logic, AI, and psychological reality into a unified system.
Our final entry connects brain development and complex cognitive deficits, dyslexia. This is defined as a developmental disorder of reading rooted in abnormal brain development, usually clinically manifest in early school years, though the underlying neuroanatomical changes exist prenatally.
It is the most common learning disorder, with a prevalence around 4 to 5%. The clinical profile is complex. Reading achievement is substantially below expectations given age and education, and it often coexists with subtle problems in writing, arithmetic, verbal memory, motor dysfunction, and sometimes attention deficits.
The most robust etiological hypothesis remains the phonological processing difficulty processing the sounds of speech. Reading requires mapping visual symbols onto a normal sound structure, and if that sound structure is ambiguous, reading acquisition fails.
This leads to the more comprehensive temporal processing hypothesis, which tries to unify the perceptual and cognitive symptoms. It suggests the core deficit is in processing rapidly changing stimuli, both visual and auditory.
And this temporal deficit ties directly to the visual system dysfunction hypothesis.
Exactly. Dyslexics often show abnormalities in visual perception consistent with dysfunction of the magnocellular pathway, which is responsible for rapid temporal processing and motion detection. Functional MRI studies confirm this, showing the motion perception area, MT, does not activate normally in dyslexic subjects. The inability to rapidly parse visual information affects reading stability.
But the anatomical findings are the most striking, showing the disorder is rooted in developmental anomalies. The first is the failure of normal planum temporalis symmetry.
The planum temporale, a language-related area, typically shows a size asymmetry in non-dyslexic brains. Dyslexic brains often fail to develop this standard asymmetric pattern, suggesting a disturbed pattern of hemispheric specialization during development.
Second, we find cortical ectopias.
These are subtle focal changes in the lamination of the cerebral cortex, small, displaced nests of neurons and glia, often found more commonly in the left hemisphere. They reflect disturbances in neuronal migration that occurred during fetal development.
And third, changes are found deep inside the sensory relay system. Thalamic neuron size anomalies.
Neurons in the sensory nuclei, particularly the visual lateral geniculate nucleus and the auditory medial geniculate nucleus, are affected. There's a shift toward an excess of small neurons and a paucity of large neurons in the left hemisphere MGN. The magnocellular layers, which are responsible for processing rapid, transient signals, are specifically degraded.
So if the MGN neurons responsible for rapid auditory processing are smaller and fewer, they can't transmit sound timing information effectively to the cortex. This means the individual struggles to parse the rapid acoustic changes necessary to break the speech stream into distinct phonemes.
And this complex chain, from genetic influence to migration and size anomalies to abnormal thalamocortical connections, and finally to a functional deficit in perceptual timing, is what underlies the failure to develop robust phonology and subsequently reading fluency.
Dyslexia thus provides an incredibly powerful case study, linking specific, subtle neuroanatomical anomalies originating in fetal development directly to complex, high-level cognitive deficits years later.
That truly was an exhaustive traverse of the cognitive landscape,
Yeah.
all within the span of a single alphabetical section. The sheer conceptual diversity is astounding.
It really is.
We move from the external social structures that define our understanding, like the cultural information economy and the rules of discourse and dominance.
And we anchored ourselves in the ultimate biological foundation provided by Darwin. We explored the fundamental questions of representation and structure, from the microscopic organizational rules of distinctive features and the debate over distributed representation right up to the architectural tensions defined by domain specificity and developmental anomalies like dyslexia.
But I think the most important conceptual convergence we identified throughout this deep dive is the tension between the optimal normative ideals, the mathematical purity of dynamic programming, rational choice theory, and deductive logic, and the often messy, contextual, and empirically observed reality of human cognition.
Right. Decision-making is systematically governed by loss aversion. Deductive reasoning is constantly overridden by conversational pragmatics. And our search for internal coherence leads to the irrational self-justification of cognitive dissonance. This observed reality forces cognitive science to rely on models that capture continuous, context-dependent change, whether in the dynamic semantics of language or the dynamic approaches modeling intelligence itself.
We've used highly mechanistic and computational language to describe everything from the complex inference system required for depth perception to the neurochemical shift that entirely dictates our state of dreaming.
So, given the power of computational and dynamic systems theory to provide a complete mechanistic description of both complex external physical phenomena and our deepest internal subjective cognitive experiences, what boundary, if any, still separates our understanding of the functioning mind from the mechanics of the physical world? That's the question that this entire field and this particular deep dive leaves you with.
A perfect thought to end on. Thank you for joining us for this deep exploration of the foundational concepts of cognitive science.
We hope you feel thoroughly well informed. Thank you, and we'll catch you on the next deep dive.